So we're going to be talking about continuity, which basically means that we're trying to figure out if a function is continuous. And I'm going to give you the definition. There's a rule about continuity and what makes a function continuous. And then we're going to look at the sheet I gave you, and we're going to do some examples from that sheet. So basically what has to happen for a function to be continuous at x equals a is that the limit as x approaches a of f of x has to equal f of a. So this is saying that whatever the limit is, that it has to equal the value of the function. And basically that means three things occur. First, the limit exists. And that means that you've thought about the limit from both sides of a. Second, it means that the function value exists. That means that there is a point at f of a. So f of a equals something. There is a point there. It's not just an open circle or an asymptote. The third thing that has to be true is that the limit as x approaches a has to equal f of a. So there has to be a limit, there has to be a value of the function, and then the two things have to be the same. So now let's look at some graphs. And in the examples, it says for you to determine if it's continuous at the marked point, and if it's not continuous, to tell which of the three rules that makes it not continuous. So A is not continuous, and one way I can tell is that at x equals 3, those two things do not connect. So when I think about the three rules, the first rule says the limit as x approaches 3 has to exist. Well, the limit doesn't exist because as I approach 3 from the left, I'm approaching the hole, and as I approach 3 from the right, I'm approaching the point, and they're two different things. Just FYI, f of 3 does exist because there's a point there, and whatever that value is, that would be f of 3. So the answer is that it's not continuous, and the reason is because the limit as you approach 3 doesn't exist. Alright, on B. This particular one, we're trying to figure out what's going on at 1, and I notice that as I approach 1 from the left and the right, I'm approaching the hole. So the limit does exist. However, there's not a value of f of x at 1. So f of 1 doesn't exist because there's not a point. It could be above, or it could be below, or it could be that hole filled in. But because the function value doesn't exist, it's not continuous. And the way that I'm describing this, if I ask you why something's not continuous, you're going to have to tell me one of these rules that make it not continuous. If it is, you're just going to say, oh yes, it's continuous because the limit equals the value of the function. So this is one of those things in calculus where there are words and you sort of have to describe it using those words. Even though it's clear that continuous means that if you're drawing the graph that you don't have to lift up your pencil to finish the graph. Alright, C. So the limit exists because it approaches that hole at 0. The value of the function exists because there is a point there. But this one isn't continuous because the limit as you approach 0 doesn't equal the value of the function at 0. Those two things do exist, but they're not the same. Alright, this one, next one on D, it's kind of strange. There's a 4 there. Maybe that's where 4 is located. It really doesn't matter which point I pick on this whole graph. It is continuous. But 4 must be the place it's really interested in, and what you do is you just say the limit as I approach 4 equals f of 4. And that's your definition, so it's enough to say that to make it be continuous. All right, E is not continuous at 2 because it doesn't connect. This thing right here is supposed to be an asymptote. I know it's kind of weird that that line is there, but I think that's supposed to be an asymptote. And what I notice is that as I try to find the limit, because usually that's the first thing I do is try to find the limit, they're approaching 2 different values. So the limit as x approaches 2 doesn't exist. Also, f of 2 doesn't exist. So really, either one of those reasons would be okay on that one because both of those are true. -1 is on f is very, very similar. I don't even understand what that graph is doing and what's going on there around -1. But same reasoning applies on E as on F. And so that one is not continuous. I'm going to let you finish G and let you finish H. Basically, you just need to tell me if it's continuous or discontinuous, and then tell me why. Okay, the next examples tell us to find out where places that graphs would be not continuous. Places that are not continuous would be places where there's holes or asymptotes. So on A, there's not any places where that would be discontinuous because that's just a parabola. It's got x squared as the highest power. It's a parabola. It's going to be continuous everywhere. On B, this one's not going to be continuous wherever the bottom is equal to 0. So you set the bottom equal to 0 and you solve. Now I do realize that if I would have factored this, x minus 2's would cancel. That means there's a hole at 2 and a vertical asymptote at -2. Well, when we're talking about discontinuity, we're talking about holes and asymptotes. So both plus and minus 2 would be places where it's not continuous. F is a cube root, and I don't know if you remember what cube roots look like, but they look kind of like that, and they just keep going. So there is not a place on that one where there's a discontinuity. It's also always continuous. Alright, D with square roots. Square roots normally start somewhere and go, but because this is square root of something of x squared, it's kind of strange. So what I'm going to do is I'm going to say that x squared minus x minus 6 has to be greater than 0, because I know that whatever's underneath that square root has to be positive for there to be a function and for the graph to work. So then I factor it, and I find out that 3 and -2 are the places where it might be discontinuous, and you can plug in numbers in between those values and outside of those values, and what you'll find out, like if I plug in a 4, I would get 16 minus 4, which is 12. 12 minus 6 is 6. Square root of 6 works. So if I plugged in a 4, which is something after 3, bigger than 3, then the graph would work. But if I plug in like a 0, which is a number between -2 and 3, I get square root of -6, which doesn't work. So what that means is that this particular graph is discontinuous everywhere between -2 and 3, and also at -2 and at 3, which is why there's brackets, because at those values the graph just sort of stops and there's not another side to the graph to find the limit. Alright, next example 3, example 4, example 5, and example 6. The question here is to figure out whether these particular ones are continuous or discontinuous. And the way to figure it out is to think about their limit and to think about the value of the function. So on example 3, I'm going to find the limit as I approach 1. And the way I'm going to do that is I'm going to plug in 1 there. So 1 minus 3 is -2. I'm going to plug in 1 there, and 0. So that means that the limit as x approaches 1 does not exist because the limit on the left is -2 and the limit on the right is 0. So this one is not continuous. Example 4. I'm going to do something similar. I'm going to plug in -2 there. -2 squared is 4. 4 plus 3 times -2, so that's 4 minus 6 is -2. -2 minus -2 is -4. Plug in -2 there, so it's negative, and then -2 squared, so -4. So the limit there does exist. So the limit as x approaches -2 is -4. The question is, does f of -2 exist? Well, f of -2 is wherever -2 is on the x values and plugged in. You know what? It's also the same. So this graph is continuous because the limit as x approaches -2 is equal to the value at -2. Alright, example 5. I'm going to plug in a -1, and I would get 3 to the negative -1 because it already has a negative, and then -1. So that's 3 to the +1 minus 1, so that's 2. Plug in -1 on the bottom, that's 1 over 0. I know that that has to do with the vertical asymptote though, because that -1 would be where there's an asymptote. So this one is either probably approaching infinity or negative infinity on the left side of -1, since we're talking about less than -1. So it's undefined, but definitely not equal to 2. So since the limit as x approaches -1 does not exist, this one is not continuous. On this second one, or example 6, I really just care about this part of it as far as the limit is concerned. And we've talked about that, how that's the graph with just an open circle. And this part right here fills in my hole. So what that really does is tell me that f of 4, if I plug in a 4 there, would be 1 over 3 times 4 minus 4. So 1 over 8. But as far as the limit's concerned, I need to find the limit of that. And so I'm going to go ahead and factor. And then I can cancel, so I get, it's 1 over x plus 4. And I'm trying to find the limit as I approach 4, because that's the value where it changes. And I get 1/8. Well, lo and behold, the limit equals the value of the function, so this one is continuous. And as far as the work goes, I'm needing you to show me that the limit and the function are the same in order to show me it's continuous. You just can't say, oh, it's continuous. You got to show me some of that work. Now, 7, 8, and 9, because I don't have room right there to write it, I'm going to write it on a slide, but it'll be those problems. Alright, on this one, what we're trying to figure out is what k is. What we want to know is what k is that makes this continuous. Well, in order for this to be continuous, basically what has to happen is the limit has to be existing, and at the value where it changes, that has to work. Well, since all of these have a greater than or equal to and a less than, that means I really just won't care about the limit, because the place where it's equal will give us the value of the function. So basically what I want to do is I'm going to plug in 1 for all the x's, because that's the place I'm changing. So it'd be 3 times 1 plus 2 equals 2k minus 1. And then I just solve for k. So I get 5 equals 2k minus 1. Add your 1, so 2k is 6. And on that one, that means k is 3. And that's all you have to do. Number 8. Again, to figure out what k would be to make it continuous, I'm just going to plug in a 2 for all the x's. So k times 2 squared, which is 4, equals k times 2 minus b. So really we have 4k equals 2k minus, and that is not a b, that's a 6. Subtract your 2k, divide by 2. So k is negative 3. And finally, number 8. I'm going to plug in a 1 for x, and I'm going to set the two things equal, which would give us the same value. Now, because k squared is in the problem, I need everything to be on one side. That's just 1k or k, so I'm going to subtract it over. Because in order to solve it, I'm going to have to factor. Find the factors of 12 that add to give me negative 1. That would be negative 4 and positive 3. And so that means that k is 4 or negative 3. Because both of those, when I plug them in, would give me the same values. Last but not least, I just wanted to tell you about these 3 words. A step function and a jump function are pretty much the same. They are like a piecewise function where you start on one piece and you gotta like step over it to get to the other piece. Something like that is a step or a jump function. A removable function is a function where there's a hole, like where there's a graph and there's just a hole in it. There may or may not be a point somewhere else, but that's called a removable function. And I was just like, if it ever talks about like what kind of function is it that makes it continuous or discontinuous, these are the types of discontinuities in functions. There's one more kind, which I didn't list at the bottom, but it's called infinite. And as you can imagine, an infinite discontinuity is a place where there would be a vertical asymptote. So at x equals 0 on that one's an infinite discontinuity. Enjoy the rest of your weekend.